Hey guys again. Here's the last video for this lecture for today. And the starting point with this example here, when we are given 10 nanocoulomb charge with a small mass, 20 microgram, and is located at 200 volt as initial place. And then sometimes later, it is located at 0 volt electrical potentials. And they ask you to write down the expression for the initial energy of the charge, and then they ask you to find the final speed of the charge. Okay, start to solve this problem here. Here is some strategies you can use it as a guidelines when you solve a problem regarding for the electrical potentials. The first one is draw the pictures, what your pictures you have it, and find where is the place initial and the final locations, and then decide do you have any component in y directions, identify known and unknown, and determine the initial and final energy, and use the conservation of energy format. And from that one, you can find any unknown that you ask to identify. So let's apply for in this strategy for this particular example. So the first one, let's decide which our initial positions. First one, here is the initial positions, which has at the rest, which mean VI is just 0 meter per second. After certain time, and the speed V final, that's why I don't have it. And this one is the unknown value. So that's the target I wanted to identify. Okay. So basically, we're gonna start from the initial positions at the rest. So what do we have? Here is do we have kinetical energy? Is we have the electrical or electric potential energy. And the rest one here, just keep it in your mind, the kinetical energy, it is K, it's basically a half mv square, whereas the V is a velocity, not the volt. Let's keep it in quick reminder for you. This one is velocity. So I started in the initial, so that means I don't have any component for the kinetical energy. The only component, since I have electrical potentials, I have a charge. So in this case, I have electrical energy component. And the total, just add them two together, so you end up with the total energy that you have. Okay? And in final situations, that scenario is different. The charge has already speed, so they end up with the speed. That means it has kinetical energy. So this is the kinetical energy, and it has 0 volt, mean it doesn't have any electrical potential energy, and the equivalent or the total one, just adding those together to find that total energy. Okay, so you can use this is initial positions, the initial energy, and this is the final energy. So let's write down as an equation right now. So let's start from the EI, which is the initial energy, which basically the Ki plus U electrical I. So you can call it E initial one. So let's replace those values. Right now, I have kinetical energy a half mass multiplied by V square, let's call it VI, plus this is the electrical potential energy, basically just the Q times VI, whereas V here, it is volt. Okay, so now here we have 0. Since we don't have initial volt, it will be 0. So you end up with this equations, the initial energy equal Q times VI, where is the VI equal to 100. Okay? So this is the equations number 1 for the initial energy. Let's find the same way, or we can calculate as a numerical value, since we have the energy, the charge, just 10 nanocoulomb. times how much we have 200 volt, and this calculation end up with this 2 minus 3, so we have 2 power to the minus 6 joule. That's the initial energy in that location, which we'll write down this one here. Now, similarly, we're gonna find the final energy, E final, equals the K final, not I, sorry, and plus U electrical potential final value, which depends about the electrical potential value at that location, E final. And we have here is the half M multiply V final square, which this value here, I don't have it yet, plus Q times V final. Where is the V final right now? Voltage potential at the location or the final location. Multiply by V final. And this one will be equal 0. I said because the voltage here is equal 0, this value here. So we end up with the formula E final. It has a half mv square, V final. This is the equations number 2. And now the last part here, we need to apply the conservation energy, which lead to the EI equal E final. So from here, EI, we have the value, we find out it is 2.0 power to the minus 6 joule. Minus 6 joule as a final equal a half multiplied by M. We have 20 gram. So here is the 20 gram power to the minus 6. This one is the gram. Multiply by, I need to find to the kilogram. Multiply by 1 kilogram, 1,000 gram. Multiply by V final square. So using solving this problem here or this equations here, one unknown, it's V square. We end up with the V, let's type it here, V as a final value equal 14 meter per second. That's the formula. We end up with the final answer in that situations. So this is the first problem here. And let's see what we have next. Here is what we have next. We're gonna just kind of introduce here the concept what we call the electron volt, which is usually basic. This is a unit to measure very small quantity of energy. So the joule, that's our energy unit, usually it's used in mechanical or the dynamic energy. It's very large value. But here we are dealing with the very small quantity of energy resulting from the charge. So this is the good to use the good domain or good scale to represent that value. That's the definition of the electron volt comes from. Now, what the electron volt as a value, it just move the charge for 0 volt to 1 volt, or basically delta V, or the change in the electrical potential 1 volt. So which means from 0 volt to 1 volt, or for example, from 1000 volt to 1001. So here in this example, just explain what we mean by the electron volt and how we represent it. Even I have two situations. I had charge, the negative charge from the 0 volt to the 1 volt. And the second one, we have a charge from the 15 volt to the 16 volt as the final position. So we'll calculate the energy in two situations, and we'll see how much end up with that case. So we have here is the initial locations or initial positions, and the second one we have the final locations at 1 volt. So here is the initial, and here is the final in this case, and the same one here is the initial, and here is the final. We're gonna just start to write down our equations, energy or the initial energy, which basically it is Ki plus UEI. And we have here is the in initial situations, here is the equal 0 since we have 0 volt. And regarding for from the rest, so this is one velocity equals 0. So I end up with the 0 joule as the initial energy. Let's calculate the final one, the final energy. We have Kf plus UE final. So in that situation here, we have Kf plus Q multiplied by V, which in this case 1 volt. 1 volt. Okay, so this is the equations number 1, and this is the equations number 2. We end up with the Kf as the kinetical energy in this case is equal, basically it will be, here is the minus, will be end up with the minus Q, Q1 with the Q1 point, sorry, this one, 1.6 power to the minus 19 as a charge, and that one represent 1 electron volt as the unit to measure this one here. Sorry to miss the unit for this one. Here is the joule. So the same concept here. If you calculate the EI in first place, and the EI here, and from the rest, so the rest here, the Ki equals 0. Okay, and move from the 15. So the only component that I have, the Q times VI, whereas VI is 15. And the second one, Q final, it's basically Kf, because I don't have the final velocity, plus Q times V final. And let's see, is number 1, and here is the number 2. And now just we a quantity that one, so to find the kinetical volt, which basically take Q here and the Q here, you can take the Q outside, and you end up V final minus V initial, which basically Q times delta V. Delta V, it's 15 minus, here is the minus 2, and delta V equal Q, which minus 1.6 power to the minus 19 times 16 minus 15. You end up with the 1. You end up with the 1.6 power to the minus 19 joule, which that one represent 10 electrovolt. So we end up with this value here, the same value, the same energy that requirement to the move the charge one electrical potential unit. Okay, it doesn't matter from 0 to 1 or any other two value. Just introductory to the electronovolts. Okay. Last example here before we move. We just here straightforward representations for if we have what is the change of the electrical potential energy. So basically we asking to find, ask you to find delta U, okay, between A and B. So this electrical here for the A, B, for the potential energy for the 3 nanovolt. So basically that's the delta dq is equal the same formula for Q. Sorry for this line. Here is the Q delta V A B. Okay. A B. Where is the delta VB in that situation is here? Required from the low energy from the point A to point B. So the final it's point B. So equal VB minus VA. So I have a Q 3 nanocoulomb. So I need to find the delta VBA, which basically I need to find VB and VA. That's I want to identify. So let's go back for the formula for the volt. Change the color. Let's use this one. Here is the volt. The original formula, it is just U divided by Q. And here is the equal K, Q divided by R. And here is the, let's call this one RA. And this one is the RB. If you want to write it in the, with the meter unit, 0.015 meters, and this one 0.05 meter. So I have that value. Now let's find delta V. Here is the delta V. VA or the VB, it's basically K multiplied by Q divided by RB. RB minus VA, K, Q divided by RA. Let's take the Q and the K outside. Here is the K times Q times Q. What I have the rest, 1 over RB minus 1 over RA. Let's plug the numbers. K, it's 9.0 power to the 9 meter square divided by coulomb square, multiply by charge that we have. We have here is 25 nano times 25 power to the minus 9 coulomb, and subtracted or the multiplication by 1.1015 meters minus 1.05 meter. You can end up with that calculations here. If my calculation is right, give you this value. It's 10,500 volt. Once I find this one, I can go back to the equations number 1 here to find delta or the a change in electrical potential energy that required the charge move from the A to B. Q, what I have it, is 3 nano, power to the minus 9 coulomb. Times V, we have 10,500 volt. And for this calculations, if you end up with that calculations close to the 3.2 power, here is the minus 6.5. So this one is the 10 minus 5. I think so. I am right. Just make sure, guys, you make the calculation for this one, and this one should be joule as a unit. Okay. This is the last example I wanna solve it or sharing with you in this lectures, and we're done for this lecture for today. Thank you so much, guys.